So this is part 2 of lesson 2.2. So as you recall from our free body diagrams, we, usually saw 4 main forces on each of those 3 free body diagrams. So these forces, or these types of forces, these are your, let me get my pen on. These are your most common ones, okay? So most times, often or not, you will see these following 4. Okay, so the first one is called the normal force. So we denote this as F subscript capital N. Again, if you put a lowercase, that's technically not true. So please be sure to follow through with the same notation. Again, we use capital N for Newton. That is the unit of all forces. Our next one is F of G, which is the force of gravity, which we also consider to be weight. And that makes sense because the force of gravity is the thing that's acting on us is gravity, and that's related to our mass, which we call our weight. Okay, here you might see it be here you might see weight be just W, or sometimes you might see F with this lowercase g. That is okay. The next one is Fa, which is our force applied. Again, notice that the unit for the applied force is a Newton. And lastly, we have a frictional force, which again has the unit of newtons. Makes sense because all forces will have the unit of newtons, which is represented as a capital N in shorthand notation. If you take a look, we have all 4 of these guys right here: the normal force, force applied, force of gravity, frictional force. Okay. We do have some other types of forces. These are called the tension force, which we denote as Ft, the spring force, which is Fs, air resistance force, which is Far, electrical force, which is Fe, magnetic force, which is F of M, and the buoyant force, which is Fb. So I'm just going to give you a heads up. The ones that we will actually be talking about later on in this class are the spring force, air resistance, electrical force. We won't really be talking about the magnetic force in super detail, but we will mention it when we do talk about magnets. And for those of you who are not familiar with buoyant, if you ever heard of the word buoyancy, it just has to refer to water. So if an object is put in water, this is the force that it experiences, the buoyant force. That's all. Okay? So based on the free body diagrams about the different types of motion from the previous slide, which scenarios depict unbalanced forces and which scenarios depict balanced forces? So if you recall, if we go back, we know that, and I'll use the highlighter on this, I'll make this the size smaller. We saw that F of N right here was the same thing as F of G. So they're the same size. So they cross out because they have the same magnitude and they point in the opposite directions. Same thing with constant velocity. We see F of G and F of N, they're able to cancel out because they're the same size, or they have the same magnitude and they point in opposite directions. And the same thing with F of F and Fa. Again, they have the same magnitude, they're pointing in the opposite directions, they will cancel out. However, if you look at acceleration, F of G cancels out with F of N as normal, great. But if you notice here, we have FF and FA. FA is clearly a lot longer than FF, which means that FF does not equal FA, and therefore you have an unbalanced force going on here. All these other ones are considered balanced. So at rest and constant velocity or balanced forces are being depicted on the free body diagrams because every single force on that free body diagram is the same length in terms of their specific direction. So my vertical forces, they cancel out. My horizontal forces, they cancel out. Here, whereas acceleration, only the vertical forces cancel out, but the horizontal forces, the frictional force, and the force applied, they are unable to cancel out. Therefore, that is considered an unbalanced force. So here, I will write unbalanced is acceleration, and balanced is at rest, and CV, which is just constant velocity. So balance means these forces all cancel out, whereas unbalanced, these forces do not cancel out. Okay? So if we go on to this next example, we're going to refer to what that excess or that leftover remainder of the force applied is from our free body diagram, right? We have this extra bit here, right? Because we are a little bit longer, so we're going to be left with a little bit more. We refer to that piece as a net force, and what a net force is just the sum of all the forces acting on the free body diagram, okay? So this symbol right here is known as sigma. If we're saying the sum of all forces, that means that this represents addition, okay? Sum is the word of addition, okay? So essentially, this is just the final force taking into account all the other forces that are acting on the object, and we call that the resultant force, okay? So think about when we talked about resultants in Unit 1, what did they mean? So now we'll work on an example. So if I have 15 going towards the left, 15 newtons going towards the left, I have 20 newton force going towards the right. So let's talk about a number line. So anything going to the right is positive, anything going to the left is negative. So a net force, right, F net, which is how we denote it, is sigma F, right, the sum of all forces. So we say F net equals 20 newtons plus a minus 15 newtons. Why do we do this? Why do we put that minus sign there? Because we are saying that the 15 newtons is pointing in a negative direction. So therefore, when we do the math, we should see that we end up with a net force of 5 newtons. It is positive, meaning that, right, I have a little bit right here. This is my resultant. Because it is positive, we know it's moving towards the right. That's number one. Number two, that means my acceleration is going in this direction as well. Okay, so the acceleration follows your net force, which is why I'm saying whatever side has more, that's the side that the acceleration is occurring on. So let's practice these. We're going to write down the magnitude and the direction of the net force. So number one, we have the force of tension is 1200 newtons going towards up, and then we have the force of gravity going down with 800 newtons. So again, we go F net, and we know that anything going down is negative, anything going up is positive. Think of your y-axis in math. Anything going towards the right is positive, anything going towards the left is negative. Again, think of your x-axis in math. So F net equals sigma F. F net equals 1200 newtons plus a minus 800 newtons. You should get an F net of positive 400 newtons. And that makes sense because you have more on top than you do the bottom. So we know what's going up, right? So here we have air resistance going up with 600 newtons and the force of gravity pulling down with 800 newtons. So F net equals 600 newtons plus a minus 800 newtons. So our net force is now going to be negative 200 newtons. This negative sign doesn't necessarily mean it's a negative number. This just means it's moving downward. Okay? Or let's not even put the word moving. That just means it's a downward direction of the net force, which should make sense because you have more going down in the force of gravity than you do in the up vector of air resistance. Now finally, number 3 looks a little hard because you have the 3 vectors and it looks a little confusing. But let's take it one step at a time. So let's look at the up and down. So we have the normal force, we have 50 newtons, and we have the force of gravity, which is 50 newtons. So F net, right, and we're only going to do the up first. Okay, so I'm going to label it up. F net equals 50 newtons minus, or plus, excuse me, minus of 50 newtons. So if you do 50 plus negative 50, essentially you're just going to get a net force in the vertical direction of 0 newtons. So that means that these guys cancel out. So then my net force is simply just 20 newtons to the left. Okay? That's all that is, because that's the only thing that's left over, the force of friction. It's the only thing that's left. There's nothing opposing the force of friction, so that is the net force. Okay? And it is moving in the left direction, which